In this video, I'm going to discuss conic sections. So here we have a couple curves. We've got an ellipse, a parabola, and a hyperbola. So all of these can be related to each other through the idea of conic sections. So I'm going to hop into Blender, which is a free, open source 3D modeling and animation program. If you're interested in learning more about Blender, I have a YouTube channel where I do beginner tutorials. You can check out a link there in the description. So here what I've got is a cone that I've mirrored on the vertical axis so that they're mirrored across this, this vertex here at the apex of the cone. This is exactly what we mean by conic sections. We are going to use a plane and slice that through the cones in order to create these shapes, the ellipse, the parabola, and hyperbola. We're going to use this to show that all of these shapes can be thought of as sort of cuts through these cones that we're making with this plane. So as you can see, I can move this plane around and we can see different shapes cut into the plane by the surface of the cone. I'm going to add a few things to this plane so that we can actually sort of save the cuts that we're making. So I'm going to add a modifier here. I'm going to use the cone as the object, and then as we move this through, it will actually change the plane itself and cut that conic section into your plane. So we'll be able to apply those and sort of pull those out. So I'm just going to make a copy of this plane so that we can then apply that modifier and have the conic section cut into the plane and be able to move it away so we can see what's going on. Right now I'll just hide that one. And so let's change the rotation on this right here. Okay, and so then with the plane sort of horizontal to the cones in this way, when we move it up and down, you can see that we end up with a circle being made. I'll go ahead and apply this. And then when we move this away, we should still have that circle that we've cut into the plane, like so. So as you can see there, we were able to make a circle just by having it like that. So let's get another plane. And then if we center up on this, and then if we tilt the plane, just rotate it a little bit. So you can see here with the circle, then if we tilt the plane, then we can get an ellipse. So we can see that circle is really just a special case of making an ellipse where there's no tilt or eccentricity to the plane as it intersects the cones. But let's raise this up a bit, make this a little bit larger. And then we'll go ahead and apply this. Move it off here. Now you'll see that we have a circle and an ellipse. So let's keep going with this and see which other of these shapes we can have emerge just by reconfiguring how the plane is sort of cutting our cone. So here at the angle, using sort of this 45-degree angle here, go ahead and we'll just move this up. This is going to give us a parabola. So you can see that that was our plane sort of not fully encompassing the size of our cone. So just here, the plane was a little bit smaller and didn't extend around the full sort of surface of the cone. And we get this nice little parabola cut into our plane. And so now in order to do a hyperbola, which is the only one we're missing at this point, we're going to tilt this a little bit different so that we're getting like this. set 90 degrees like that. And now you can see the hyperbola starting to emerge. So we do like that. Let's just bring it in here just to make it nice. I'm just going to shrink it down just a little bit so it looks nice when we cut it. And now I'll go ahead and apply our modifier, and we should have a nice hyperbola. Let's move that over, center up. And so as you can see, just by using this plane, we have been able to cut our sort of double cone there in such a way that we are able to produce our ellipse, our parabola, and our hyperbola. Okay, so those are sort of the standard conics there. I've included that circle as a special case of the ellipse, but there are actually a few other special cases that we can look at that are known as degenerate conics. So that's where we're sort of pushing this idea to an extreme, and we get to a configuration that gives us something kind of interesting. So if we set this as being 90 degrees so that our plane is vertical, let's just shrink it down just a little bit so that it fits nicely. And then we're going to move it over so that it is exactly on center. So now our plane is centered up with our cone. So where the two cones meet is actually the center of our plane. So let's go ahead and just make a copy of that. And then we'll apply the modifier here so we can see what we have left. And this is going to give us this section here, which is going to appear as two straight lines intersecting. And that's just because we're just then, instead of getting the curvature, we're just sort of getting the flat head-on look, one could think, sort of like this. So I've put this into a front orthographic projection, so there's no perspective. We're just getting a flat image here of our cones. And so our conic section in this point, this is a degenerate hyperbola. So in sort of the extreme case, when you're exactly cutting your two cones in half, you end up with these two straight lines crossing. So another degenerate conic is made when we put our plane horizontal to our cones. So I'm going to set this back to 0, which is going to make our plane horizontal. And now our plane is only intersecting our cones at the apex where they are joined. So this is only going to generate a single point. I don't know if the Boolean is going to work with this because it's not technically a polygon, but let's give it a try and just see if we actually can see anything. So when we apply this, move it away, I don't know if we'll actually see anything because it's just a point. Yeah, I think the gizmo is covering up any little hole in it, but if we go into edit mode, we can see if it's made any adjustments to the, yep. So these two lines here did not exist on the sort of the default plane, and the program put those in so that it could identify and then sort of cut out the point here that's being covered up by the transform gizmo. But that's how you make a point. A point is a degenerate circle, essentially. It's a circle with radius 0, and it corresponds to when we have the plane completely horizontal and just going through the apex of those two cones. So there's two more, and they have to do with parabolas. So let's get a copy of our plane again. Hide that. And so now we want to set our plane to a 45-degree angle, and that just corresponds to the angle sort of our cone here, of how the cone is opening up. And so the idea here is that we are only getting a single line from this cone intersecting this plane. Again, I don't know if the program is really going to be able to render this for us, but you can sort of see as I move that there's like a little glitchy line that appears. And that's because these two surfaces, there you can see it's sort of dotted. That's because the surface of the plane and the surface of the the cones are trying to occupy this same space here, so the computer doesn't know which one to render. But if we simply apply our modifier, we should be able to look in the edit mode and see that it has indeed put a line through our plane. Let's move this out of the way. Center up on it. And so there you can see now it has actually cut our plane in half with a line right down the middle. So there's one more degenerate conic that we can do. We're going to imagine that the apex of the cone is an infinite distance away from where we're taking the slice. What that ends up doing is making it so we end up with two parallel lines going through our plane. Unfortunately, this is not something that I can demonstrate in the computer, as the computer is not able to imagine this at infinity. So that's one that that you'll have to do in your head and sort of come to grips with that. But that's the explanation on how to get two parallel lines, is to imagine that the apex of the cone is at infinity, and we are very, very, very far away from that point when we're taking our slice. So now, seeing how these different shapes can be related geometrically as conic sections, that then sort of makes me wonder, can we relate them algebraically? We know some equations for circles and for ellipses and for parabolas and for hyperbolas. Can we relate the formulas that generate these shapes to each other and make sort of a generalized formula that will handle all of them? Turns out we can. That generalized conic formula is ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, where a, b, c, d, e, and f are constants, and x and y are your x and y coordinates on your xy plane. Okay, I'm going to go into Desmos now, which is a free online graphing calculator. And we're going to play around with this formula that I've got plugged in up here in the upper left. You'll see I've got this full conic section formula plugged in, and I've got sliders put in order to manipulate the various constants in the formula. And then I've got a few other things down here that we can look at as well. This is the formula right now for a circle, but you can make that into an ellipse by changing the a and b parameters. And then we've also got this other formula here, which is the formula for a hyperbola. And again, we can adjust that. And you can sort of see how the hyperbola and the ellipse are related to each other. So that's kind of cool. And now let's take a look at using the general formula here and see if we can extract the circle / ellipse and the hyperbola formulas from it by changing these coefficients. So when I turn that on, we'll turn off the circle. So in the current configuration, I've got it outputting a circle. So I've got a 1 in the a coefficient, a 0 in the b, a 1 in the c, zeros for both d and e, and then a -1 for the f. And by doing a little bit of algebra, you can see how that then produces this formula here, giving us the same shape, the circle. So you can see green there is with this formula, and the red is with this. And again, by changing these parameters, you can change the shape and make it into an ellipse. So in order to do the hyperbola, we want to change one thing and make that negative. And that one little change turns that ellipse into this hyperbola. All right, so let's go back to the circle there. And if we set f here to 0, that ends up giving us the central point there. Because what you've done is the f in this case ends up being the radius of the circle. And so with this here as -1, that gives us this circle of unit radius 1. And we can then By changing that, you can see it degenerate down to a point. Now let's look at the hyperbola. In order to get our degenerate conic here, we need to just make some adjustments. We just need to change f to 0 here. So we can get this. So again, we're just going to use the slider. You can see once we hit 0, then it's these two straight lines that are intersecting here at the center. And as we move it along, you see them change to either being sort of vertically oriented or horizontally oriented. But we get that degenerate conic, the sort of the X shape when f is 0. And now that brings us to our last conic, the parabola. So we can make a parabola using this combination of coefficients here. I've got the a set to 1, e set to -1, and f set to -1. Now, in order to get the single line, we can change our a parameter, and as you can see, now it is sort of getting flatter and flatter and flatter until when it is 0, it is a single line. Let's go back up here, bring the a back up to 1. And now if we adjust the e parameter, you can see that when we take that to 0, now we have our two parallel lines. And that was when we are imagining the point of the cone to be at infinity, and that sort of generates these two parallel lines. So we can see that these various curves are all sort of connected to each other by this notion of conic sections and through this generalized algebraic formula. Okay, and that'll do it for this video. Hope you enjoyed it. Thanks for watching.